In this video, I'm going to be specifically covering the conjugated systems of double bonds and how those systems interact with different electrophiles or substituting groups. And I'm also going to be covering the Diels Alder reaction. These are the two main new unique reactions for the exam one, and you need to really know them very well. So just to introduce a bit, on your reaction sheet, you'll have this section, and what you'll see is there's going to be two conditions, okay? There's going to be, they're not listed here, but there's going to be two conditions. There's going to be the kinetic condition, and there's going to be the thermodynamic condition. And depending on what condition you're in, you'll have a different unique product. And this product is determined by different factors for each one, and we'll go over that as well. The concepts is not really too heavy for this reaction. You kind of just have to understand in a general sense how it works and why a certain product is favored over the other. And to explain the background of what's required to have this reaction, this setup, is you have to have a conjugated system. And a conjugated system is any system that has conjugated double bonds, and that means double bonds that are literally back to back. Okay, so basically it provides additional stability. The more double bonds that you have that are conjugated, the more stability that those double bonds are going to have. So it allows for things like resonance structures and so on and so forth that help stabilize the entirety of the molecule and lower the energy, the total energy. And so just this is a very simple conjugated double bond system right here. We have a total of 4 carbons, 1, 2, 3, 4, and you just have 2 double bonds, and they're 1 carbon apart. So it's a double bond. So you have a pi bond, sigma bond, pi bond, sigma bond, pi bond, sigma bond, so on and so forth, and just one apart. And this is very important when it comes to resonance and stabilizing factors and stuff like that. So I'm just going to show right here the different states and different situations, and you can react this with many things. I'll go over those as well. So we have the kinetic, thermodynamic. Okay. All right. So this is the kinetic side, and this is the thermodynamic side, and it's very easy to know which one is which. You're not going to be required to recall the terms really, but it's a terminology that makes sense with what is happening in the condition. So kinetic has to do with why a certain product is formed. So this happens in low temperature environments. So the temperature is 0 degrees or colder, and then thermodynamic, as you can imply from the name, happens when the temperature is higher. So you'll see 40 degrees, you'll see maybe higher than that. Okay, so these are just two. The temperature can vary, and she can change it on the exam, but the concept is just cold versus added heat. Okay, and I left these molecules blank here for a reason, because we're going to show what happens. So I can react this. What can be on the arrow can be a variety of things. It can be, this is really big, HBr, it can be Br2, it can be MBS even. Let's see, what other things. I think these are the main ones. Okay, HBr can also be any acid, but usually you'll see HBr. So there's just a couple of things that you'll see, and just basically things that you've seen before that react with double bonds. We have dihalide. We have a acid. We have MBS. MBS is one thing. We have H2O plus. So these are the most common ones that you'll see. And essentially, we're going to be looking at the formation of a carbocation, and we're going to look at how that carbocation, the location of it, depending on the environment, right? Depending on the conditions. And what you need to know is that, so in the kinetic product, what happens is, the kinetic product always favors aka the carbocation location. Okay, so the kinetic product is always going to favor the location that forms the most stable carbocation, and that's going to determine our final product. Okay, so in this reaction right here, I have this molecule. I have to decide, you know, when I react this with any one of these things, where that NBS is the only exception where that forms a radical, but I have to decide with these other ones, where is that carbocation going to form first? So am I going to use this double bond or am I going to use this double bond? And, you know, this will be the double bond that we use because it forms the most stable carbocation first. And in any reaction, even if I was doing this one, we would still react with this one because the first step of the reaction is going to, we're always going to look at which one forms the most stable thing first. It's just that this one has a resonance structure that after the resonance structure occurs, that it prefers a different type of thing, okay? And we'll talk about this in a second. So this is the double bond that I'm going to react with because it can form a tertiary carbocation, and this one cannot, right? It can only form either a primary or a secondary. And so I'm going to have this double bond right here, and in the first step, I'm going to have this positive charge right there, right? And now I've formed my intermediate, right? And for both of these, you know, for both of these reactions, you're going to have resonance. Resonance is always occurring. Resonance is something that occurs to help stabilize a molecule. It's always happening if it can happen. And so there is a resonance state, right? So the resonance state, I'm actually going to just do this right now, is actually going to be with this one right here. Okay, so the resonance form is going to be this one, and the carbocation will come out over here. So this will come over here, this will resonate, I'll form this double bond right here, and then the carbocation will move onto the very outside. So these are the two resonance forms, okay? And this is what you're always going to be looking at when you're selecting, you know, which carbocation location I'm going to use to form my product. So for the first one, for the kinetic product, we're always looking at the location and the intermediate products, right? The resonance structures that the positive charge is on the most substituted double carbon. Okay, so this is the most substituted location. This one's tertiary. This one's primary. So I'm in 0 degrees or lower. I'm going to substitute right here. So in my answer, if I was using HBr, right, the H is going to be the first thing that's reacted. So one of these carbons is going to get H, and then the other one's going to be a carbocation, and that's going to be where the bromine, Br minus, comes and attacks and forms, right? So in my answer, I think I can have another one. All right. So in my answer, I'm going to have the one right there, and that's what I have. So that's the answer for that one. Okay, so kinetic always forms the most substituted. And this is what we refer to as the, I believe, the 1,2 product. Yes, I believe. Right? So this is the 1,2 product. And I really actually don't understand where the number is coming from. It's kind of weird, but you don't have to worry about what's the 1 and what's the 2 and what's that. That's just what they refer to as. It's 1,2. Okay, and then for this molecule over here, we'll talk about it. All right, it's going to form the 1,4 product. Okay, and that's going to be this one right here, and like that. Okay. So this is the 1,2, this is the 1,4. And the only difference between the 0 degrees or kinetic state and the 40 degrees or higher thermodynamic state is that the thermodynamic state, the kinetic state always prefers the intermediate that is most stable, right? But the thermodynamic does not care about that. The thermodynamic actually prefers the product that is most stable. So this one is dependent on the intermediate, this one is dependent on the product that we get. And the product here is going to be to determine what's the most stable product, we have to find the location of the double bond that is most substituted. So this is the most substituted double bond location. I have a tri-sub here versus a mono sub. So this is mono, This is tri. Right? So because this is the tri one, this is going to be the one that I use for my thermodynamic state reaction. And so that's how you figure out how to use each one of these things. And it's really not that bad. You just have to be careful about choosing. In both of them, you're always going to choose the double bond to react with first. That gives you the first, most stable product, right? And then you're going to do a resonance structure like I've shown here. So I chose this one first because it can form the more stable product. And then I'm going to do the resonance forms, and I'm going to compare the two. And then depending on what the condition is, I'm going to prefer either a more stable intermediate, or I'm going to prefer the more stable double bond location. And that's all there is to it. And it's not bad at all. Okay? And this would work the same way with H2O plus or Br2. You just have either an OH product on one of them, and this one would have two BRs, and this one would have just a BR, but you would be forming a radical at one of these locations instead of a carbocation. And that's all there is. Okay. So I think that covers that generally enough, so that you can do some problems on that. Now let's talk about the more challenging problem, which is Diels Alder. Okay. All right. So here's the basic setup for a Diels Alder reaction, and essentially what you need to know about Diels Alder is that it's a reaction that we use to combine essentially two molecules, and we're going to cyclize. It's going to make a cyclic system as a result. Okay, so what we require to do this is we need a conjugated system. So we have this we need two conjugated systems, but they're unique. Each one is unique. So what we have over here is what we call I hate this thing, the diene. Okay, I need to make this smaller. The diene, and then what we have over here is the dienophile. Okay, so I have the diene and I have the dienophile. The diene is characterized by, it has to have at least two conjugated double bonds. Okay, so diene, right? It's in the name. Dienophile has to have at least one double bond conjugated with what we call a withdrawing group. Okay, it can be any withdrawing group. It does not have to be a carbonyl. So I'll show you some other examples of other withdrawing groups, and this will be a very important concept for test 2. But at the moment, just focus on this. So we have to have a diene, and we have to have a dienophile. Okay, and what we're going to make at the end is a 6-member ring. All right, so we're going to be making a 6-member ring always. And is it always? I think it's always. I believe so. I believe it's always. So I have the diene. Diene here is two double bonds, and the dienophile has one double bond and it has a withdrawing group. A withdrawing group is anything that can that has a resonance structure where the flow of electrons can go out of the system. So essentially, if I resonated this double bond right here, the electrons can go outwards onto this oxygen. So anything that allows the outward flow of electrons through resonance is a withdrawing group. Okay, so you'll see many examples of this, but most of the time the example is through the carbonyl. It's the most common type of withdrawing group. Okay, and so we always form a 6-member ring consisting of these 4 carbons at least. So 3, 5, 6, and everything else. There can be things that are sticking off of these 2 over here, but anything else that's coming off of these 6 carbons are going to be on the outside of the ring. Okay, so the ring is going to be made of these 6. And what happens essentially, okay, is that the basic reaction is that I have, let's say, for example, well, there's one thing actually I need to do first before I show you this, okay? All right. So what's going to happen is the diene is going to attack the dienophile, right? And to make this more, more realistic, where the groups are oriented properly to attack in the most, I guess, energetically favorable way, we have to redraw our diene. And essentially what happens is the diene can rotate around the sigma bond right here, okay? And we will get this structure, okay? So I'm going to, I wrote these together, okay? So we're going to get this structure. And so this is the one that I'm going to be using. I'm just going to put it over it. And so what happens is one of the double bonds is going to come and it's going to attack right here, okay? And then this double bond is going to come and it's going to attack right here. And then this last double bond is going to resonate inwards right here, okay? And this is a general reaction that will always happen, okay? But what's important, and right now I'm not showing the full like range of things that you have to consider when you do this reaction. I'm just showing you the basic setup. It's not this simple, okay? So when I do this, I'm going to get a molecule like this. So I have these four right here. So I have these four, and I made a bond with this one right here. So now I have this ring that's forming. So I have this one, I have these two carbons, and this one formed a bond right there. So I get a 6-member ring as a result. And then I resonated this double bond right here. So this is where it is. Okay, and then off of this carbon right here, so let's call this 1, 2, 3, 4, 5, 6, right? And this is 5 and 6. This is 2 and 3. Okay, just to avoid some confusion. Off of 6, I have this carbonyl group, and then off of 5, I have this CH3 group. Okay, and there are more things to consider, but this is just a very general. I'm not showing any stereochemistry at the moment yet. So this shouldn't be here. So I'm not showing any stereochemistry yet. This is number 1. This is not a methyl group. So in reality, there's more factors, and I'm going to show that. So when we're doing this, there's a few things you have to consider. First thing, when we do this reaction, I have to decide how to orient my diene and dienophile, right? So in this example, I have them oriented just like this, but I could also have them oriented potentially with the dienophile kind of flipped over. So the dienophile could be flipped 180 degrees, and this group would be on the bottom. And I'll show you how that's important and how to figure that out. Okay. All right, so I changed the reaction up a bit, and I forgot to mention that this reaction is always done. All we need on the arrow is heat. Okay, so I just need these two present, and I need it in the presence of heat, and that's all that is required to make this reaction progress. So I changed this a little bit just to demonstrate the concept. Okay, so I'm going to explain two concepts here in this example. Okay, we're going to talk about something called Endo rule. And I'm also going to show you how to orient your diene and dienophile so that you get the correct product, and the most stable product. So for this reaction to progress, what we need to do is kind of imagine that I take away all the pi bonds. So all the pi bonds, right? And what we're going to do is we're going to, obviously when you take away a pi bond, you have to replace it by both a positive charge and a negative charge, right? Something's going to get the electron, something's going to become a carbocation. So whenever you take away a pi bond, you attribute a positive and negative charge to the carbons that were participating in the pi bond, okay? So hope everyone's following at the moment. All right, so if I took away all the pi bonds, this is what we get, right? And I said we have to attribute to the carbons that were participating in the pi bond, both one of them gets a positive charge, one of them gets the negative charge, and aka the electrons. So when we do this, we're going to attribute these charges based on where they are most stable. So I'm going to put them in the location where they're most stable. So we look at our stability rules. So carbocation is most stable on the more substituted carbon. So this one's going to have a positive charge, this one's going to have the negative charge. And then once you figure this out, so this is going to be, the other one has no real preference, right? The other one is just carbon here, carbon here. It's not really anything so significant. This one's going to be contributing the most to the stability, this tertiary carbocation. So once you figure out the, at least one, it'll let you figure out the remaining. So it has to alternate. And I know this might seem like kind of like weird Orgo. This is the only time in the class where I'll really be kind of vague like this and use kind of mystified organic concepts. But really, it's just you'll alternate the charges at this point. So negative, positive, this will be negative, and this will be positive. Okay, it has to alternate. And you figure out the orientation of this by just looking at where the most stable position for something is. And that's where you're going to have, it'll let you figure out, whether this is going to be positive first and this negative, or this positive first, so on and so forth. And then for this one, the rule is very much the same. So I'm looking at these locations, and so I'm going to put the charges on the location where they're most stable. So I have an oxygen here, that's where the negative charge should always be, right? So now that I have that, this is going to be negative, this is obviously positive, now this is negative, and this is positive, okay? So now I've given charges to these locations. And what's important for me at this moment is that I have to match up. Let me get a different color here. I have to match up with their opposite charge, this one and this one, to this one and this one right here. So these have to match up, but they have to be opposite, right? Because I can't put two of the same charge next to each other. They will repel each other. It's too unstable. I'm going to match the charges together, okay? So what does this mean when I have, in this case, I have the negative match with the negative, the positive match with the positive, okay? What this means is that I have to flip my dienophile, okay? So if I'm just going to erase a bit, if I flip my dienophile, I'm going to select all of this. That means I have to rotate this the other way, okay? And essentially, now obviously you can redraw this where these groups are on the the same sides facing it, okay? But essentially, I'm just trying to demonstrate here that now once I flip it, now my negative is going to match with the positive, and the positive is going to match with the negative, okay? So if I was to really draw this. I would draw it like this, just to demonstrate really quickly. Okay, so I put the O minus right here. Okay, so this is what I have really: negative, positive, negative, positive. All right, and now things are on opposite sides, or opposite charges are on the same side. And now I can do my reaction. This is how my reaction is going to take place, okay? And this is going to give me a completely different molecule than if I did the top one, right? The top one, if I do this one, this group and this group are going to be on the same half of the molecule. But this one, they're on opposite sides. So it is important for you to always do this process of labeling the charges based on where they're most stable. In the dienophile, the O is always going to have the minus, so that's easy. This one, you just have to look at, where the most stabilizing group is here. Here, I just have a carbon, but this can also be, you'll also see this potentially, right? And this is also does the same effect as if you just had a carbon group, because this can through resonance, it can stabilize a positive charge. So this is by far the most stable position still. Okay, just giving you some examples, all right? Some variations of the problem. All right, and you're going to always look at the most important contributor to stability. All right, so now that I know my orientation, now is, I'm going to erase all this mumbo jumbo right here. Okay, so now I know my orientation is like that. I'm going to redraw this molecule upside down. All right, so here's the molecule, and I'm just drawing it in the other way. I'm just going to put this over it, all right? It's not too important, how you orient these groups necessarily. We'll talk about that in a second, because in the end we're going to get a ring, and those the way the groups are oriented stereochemically off of the ring are going to follow a certain set of rules, okay? So first things first, we said this is the positive, this is the negative, this is negative, this is positive. And we said the negative, positive, negative, positive. Negative, positive, positive, negative. So they're matching, right? The whole thing is matching very nicely. I'm going to bring this a little bit closer right here. And so now all we have is, I always like to start from the negative because it makes sense to me. Negative is going to come, this little bond is going to come and it's going to attack this location. Then this one's going to come out and attack this location. And then this is going to resonate into the middle. Okay, so here's my reaction, right? Very simple. And now we're going to get a 6-member ring because I have a total of 1, 2, 3, 4, 5, 6. So it's always 6-member ring that is forming. Okay, and now let's look at what that looks like. All right, so here I have a 6-member ring. Okay, and now I need to just put all the right groups on it in the right locations. So first things first, we have our double bond that forms right here, right? And I have this methyl group that should be right here. All right. And then I have on the top over here, I have a hydrogen and I have a CH3 group. And over here, I have a hydrogen and I have this carbonyl group. Okay. And one thing you have to know, the rule that will always be followed every single time, 100% of the time, is you will always have the groups that are on the dienophile that are coming off that double bond are always going to be called in the position that we call endo. They're always going to be in the endo position. And the endo position is correlated with the dash. Okay? It's being correlated with the dash. The XO position is the wedge. Okay? So you need to know this at this moment. XO is out. This is endo is in. Okay? So it's always going to be in. So we have the endo position. I'm going to have my dash, and on that I'm going to have my CH3 group. And then on the wedge, I have the hydrogen. Very ugly, but I'll show you a cleaner one in a second. And then on the dash over here, okay, I have the carbonyl, and I have a CH3 group, and then I have obviously my hydrogen on a wedge. And this would be our answer. And the clean version of this would look like this. Alright, so here's the clean version of the answer. So here's my endo products. And they always have to look like this. So I have the dienophile groups that are in the endo positions. And this is just the way that this molecule orients so that the reaction can proceed. That it turns out that the most stable and the major product is the endo position products. Okay. Now this is the majority. This will cover the majority of your problems that you'll see, but there is one more thing. Okay. Now I've shown you. It has nothing to do with the dienophile. It has to do with the diene. Okay, and I'll show an example of that right now. All right, so let's say we have this example right here. Okay, now first things first is we need to label the positions as it, when like if we pretend that we remove all the double bonds. So if I remove all the double bonds, if I find the most stabilized locations for the positive charges and negative charges, what we'll have is this. Okay, so I'm going to look over here. If here I can't really tell, and I can't compare any of the two. So over here I can though. I have a secondary, I have a primary. I'm going to make this the positive charge, this the negative charge. That means positives over here, negatives over here. Okay, and that means over here I have negative, I have positive, negative, positive. All right. So this is just setting up how to label the charges. All right, and I label them according to where the locations is most stable. I'm going to look at the most, stability defining location, and that's going to control the orientation of where positive, negative, is it negative over here or is it positive over here, and then you follow through. So now I have this, okay? A slight difference from the last problem. I moved the methyl group from over here to over here now, okay? And when I do this reaction, right, with heat, blah, 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 I'm going to have this coming over attack over here. This will come and attack over here. And this will resonate inwards, okay? Doesn't seem too bad at the moment, right? But now let's look at the product, and the product will differ now. All right, so this is a very general version of the product. I still have to fill in a lot of things, right? We're going to make a 6-member ring. The double bond will always be right here. And I'm always going to have, you know, these things on the endo position. I haven't, you know, drawn them out yet, but we have an idea what's going to be there. So double bond's right here. I know this is on the top, so this is where the, you know, carbonyl is going to be, and this is where the carbon group is. So that's fine, right? But now the difference is the methyl group that I had on my molecule used to be on a double bond, aka did not have stereochemistry besides, you know, cis or trans. But now the methyl group is over here, and now it has to have stereochemistry, right? It's no longer on sp2 carbon, it's on sp3 carbon, and I can give it stereochemistry now, right? If it's on a ring, it's going to be on a wedge or it's going to be on a dash. And so how do you determine whether the methyl group is now going to be on a wedge or it's going to be on a dash? And the way we determine this is it's pretty simple. So anytime you have the diene, right? And let's say, you know, here's your double bonds. You're always going to have a group that's going out like this, and a group that's going out like this, potentially, right? And a group that's going out like this, and a group that's going out like this. What you need to know is that the positions that are right here are essentially kind of endo positions, okay? Endo, all right? So they're kind of endo before the reaction happens, and these are exo at the moment. All right, so they're going out. And all we have to do really is that after the reaction occurs, what was going out and what was going in, they're going to flip. So what was going out is going to go in afterwards, and what was going in is going to go out afterwards. So my methyl group was originally going outwards, right? So it's going up, right? And then afterwards, right, it's going to go in. So that means that my methyl group is going to be on a dash. And that's all there is to it. Okay, that's what you're going to be expected to know how to do in the exam. And really, it's not that bad. And most people mess up on this part because they don't know how to like determine, you know, what happens after the reaction, or what's on a wedge, what's on a dash. So that should cover you for the majority of the problems, and really should make it pretty easy. Best of luck, and do tons of practice because there's a lot of variations of this problem.